Okay, thank you. So good morning, everybody. I'm sorry that I arrived only today, actually at 1 o'clock this morning, which means that I missed the talks and the debates of yesterday and the day before. That's due to the Lufthansa strike, which prevented me from attending earlier, but also somehow it's nice to see that the Germans are also able to show this side of civilization. So let me just start with continuing on the habit of the previous speaker by flashing just one result. It's the comment I made before, namely that if you follow Bohm's idea that the influence explains or that causes, that locally causes actually the non-locality or the violation of Bell inequality, if you follow Bohm's idea that this should go at some finite speed, so not infinite but finite, could be superluminal but finite, then you can activate non-locality. So then you can also superluminally signal. Okay, so this was just a comment, and now I come to the real part of the talk, probing large entanglement. So the idea is really to see both conceptually, and I will also present some experiments, how one can go from the small, the natural place of quantum physics, to something which maybe you like to call macroscopic. You'll see I prefer to use the word large entanglement, and I'll try to define it. But so the very, very general and broad kind of questions we're going to ask is, does quantum theory extend to all scales up to the macroscopic? I know it's not well defined, but it's the kind of questions I like to address. And the other one is a more technical question. Can one master the many quantum degrees of freedom of classical objects? And these kind of questions were triggered, at least on me, by the kind of experiments we did. Now it was published last year, but the experiment was performed 2 years ago, where we had two crystals. You see these crystals with this nice kind of picture here. The crystals are about 1 centimeter long, so you can easily hold them in your hand and all that, and you can see them, and they are clearly macroscopic. And we could show that we can entangle them. Now, of course, does that has anything to do with macroscopic entanglement? I can already tell you my answer is no. But why not? After all, the crystals are clearly macroscopic, and inside these crystals you have ions, neodymium ions, that are implemented, and you have billions of them, or even more. And we cool the crystal to about 3 Kelvin so that all the ions get to the ground state. But then when we send some light in, including if it is a single photon, then this single photon gets absorbed. And that means that these very many ions get into some state which is like a W state. You know, one excited, all the others in the ground state, and a huge superposition. So we have a superposition of 1 billion ion. And we actually have a superposition of 1 billion ion here, entangled with these ones here. So how interesting is that, and how far further can we go? So let's try to ask this kind of question. So the vision is that we want to address these questions, and I think very clearly these are fascinating questions, not well defined yet, but fascinating, at least to me. And they have been fascinating since decades. Nothing new so far. But I think what is new, and which is really making it interesting now, is that these questions become timely for 2 reasons. First, because I think, in great part thanks to quantum information science, we understand quantum theory much better today. Certainly much better than in the 30s, but that's an easy statement. But also very interesting, the technology is ready now to address these kind of big questions. For instance, there's a lot of work going on nowadays on nanomechanical oscillators, where people want to show that they can be brought to the quantum mechanical ground state, and that you can also excite them and have them in superposition, possibly in the future entangled also. Plasmons is another example that involves billions of electrons. Okay, entangled diamonds, the work by Jan Wormsley's group in Oxford that made quite some noise about 1.5 years ago. Our work on the crystals, atomic ensembles, etc., etc. But of course, the questions is badly defined yet. what does it mean macroscopic, and what is quantum? What does it mean to be quantum? So let me start with the second question, which I believe is the easiest one. And I would say, okay, if we show that we have entanglement, we show that these objects really have some quantum property. We really demonstrate some quantumness of these objects. Now, for macroscopic, well, first let's move away from macroscopic and maybe just call large entanglement. I think that will become clear what I mean by why I want to move away from macroscopic, which is not well defined, and large can be defined. And just to be clear again, whether our two crystals here would count as large entanglement, no. So I want something which is going significantly beyond just having a kind of delocalized excitation between two ensembles of ions in these crystals, for instance. So what is large entanglement? So entanglement we know, and we can even measure them. No? They are measured in E-bits, entanglement bits. So large entanglement, at least one possible approach, would be just to say, well, many E-bits. If we don't have one E-bit, like in a singlet we have one E-bit, now if we have many, a large number, then that would be large, at least from that point of view. But that is probably necessary, but I'm not sure this is sufficient. Or actually, I'm pretty sure I would claim it's not sufficient. Then, I mean, you could have many singlets simply. This is not sufficient. So a second thing could be large distance. Well, we did in Geneva many experiments with large distances. It's also large in some sense, but this is not what I want to talk and discuss today. It's not the most relevant to today's talk. Now, many people would answer that large entanglement means large mass or large number of particles. And here when I say particles, I'm not thinking of photons, but particles that have some mass. I don't know, neutrinos is maybe too light, but some real particles somehow, whatever exactly it means. Some that undergo the heating process of GRW, whatever. Now this is still not enough. Even if we would have many E-bits, large distances, large masses, or large number of particles, this is probably not yet sufficient because, for instance, in our crystals, as I told you, and also in the diamond example, there are indeed many particles, billions of them, but they are just in some kind of this W state, so this kind of delocalized single excitation. So I guess another requirement for large entanglements, which makes sense, would be to have a large number of excitations. I don't want just one excitation, I want many excitations. Okay? So now we have all these criteria of being large, and very clearly you can be large, or entanglement can be large, in many different ways, and they are not exclusive. And so I think the field of large entanglement, of macroscopic entanglement, is clearly a field with many facets, and you cannot just say one is correct and the other one is incorrect. But you certainly have at least this number of facets to this question. You could also have a large number of parties, of course. And then some people would also claim that large entanglement must be very sensitive to decoherence. And certainly decoherence exists, we all know that, and there's no doubt that if the system becomes very large and complex, there will be decoherence which is difficult to master experimentally. But I want to avoid here to make a circular definition. I don't want to make a definition which is based on ultra-sensitivity to decoherence in such a way that by definition it is impossible to probe large entanglement, because if I would be able to probe it, then the answer would be, oh, you could probe it because it's not enough sensitive to decoherence. You see, I don't want to avoid the possibility of playing with large entanglement just because I have defined large entanglement as something impossible to probe. That would not be very interesting. On the other side, there is also the fact that I guess some form of decoherence probably exists always. But we'll see in the experimental example I'm going to present in a few minutes, that you don't need, or large entanglement in my sense, doesn't need to be sensitive or ultra-sensitive to every form of decoherence. It may be robust to some form and sensitive to some other form. Again, that just means there are many facets to large entanglement. Okay, and then also one should actually distinguish, okay, fermions from bosons, or let's say in a more prosaic way, qubits, including two-level atoms or two-level ions, from photons. And if you go through the literature, I didn't want to put references here because I'm sure I would miss too many references. But there are many references, so many approaches do already exist. So I'm not the first one by far to ask these kind of questions. But almost all the approaches I'm aware of, they start by assuming a large collection of qubits. It's always done in this abstract qubit language. But I'm a quantum optician, so I don't play with qubits, I play with photons. And photons are not qubits. So I need to change them. There are things that need to be adapted to the bosons, if you like, or to the photons. And so if I want now to kind of very naive starting point, let's say large means that I can see it with my naked eyes. Certainly things that I can see, that you can also see, by the way, that's large. That's a kind of natural measure, how large it has to be that we call it really large. But of course that's not so simple because, as you know, we can only see photons. We never see a qubit. Even the crystals, we don't see the crystal. Of course, we see the light which is reflected on this. I will come back to this problem, that we don't see the object directly. Okay, no way to talk about macroscopic or large entanglement without at least one slide on Schrodinger's cat. The only thing I want here to mention, since we all know about Schrödinger cat, so we start with an atom in an excited state, and this atom decays, and we go to the time when it has half decayed, halved in a quantum mechanical sense. So we have the atom in the ground state, and there is one photon that has been emitted, entangled or superposed with the case where the atom is still excited and there are no photons. And then by some local evolution, I mean all this causal chain, we get to this Schrödinger cat state, atom ground state, and the cat is dead, superposed with atom still excited and the cat still alive. So what is important here, and that's the point I want to stress here, is that we start from something which is microscopic entanglement, and we end up with something which is no longer microscopic. It's on the contrary, okay, this cat thing, certainly large. And to go from one to the other, you have local evolution. And this is something really that we can learn from Schrödinger cat. Large entanglement is not invariant under local unitaries. I have to say it took me a long time to really realize that, because in my community, quantum information, the statement that entanglement is invariant under local unitaries is, it's one of these 10 commandments that you learn, and you just never question it, and actually it is also true. I mean, entanglement cannot be created locally, or it is invariant under local transformations, under local unitaries. But when you now want to talk not about just entanglement, but large entanglement, very clearly large entanglement is not invariant under local unitaries. I mean, the Schrödinger cat shows it very well. You start from something which is very small entanglement and you bring it to a large dimension. And we're going to use that also for the experiment. So at the end, what do we want? We want something, let's say, 0 times a psi 0 plus 1 times a psi 1. And these psis, they should involve a large number of excitations and of particles. That would be already quite nice. That would start smelling like a Schrödinger cat. But it is clearly not sufficient, because that's very easy to produce. Now you just take a singlet, and next to the singlet you put an elephant. And if you do that, this state can obviously be written in that way, where psi 0 and psi 1 is just, let's say, the state 1 tensor, the elephant, and the state, okay, that's not very, I mean, the 0 and 1 are probably wrong here. And the psi 1 is the 0 times the elephant. So clearly you can very easily make such a state and indeed have a large number of excitation and particles, but this is not what we want. This is just a singlet and there is some big object standing next to it. So the next requirement that is needed here is that these psis should be distinguishable with high probability, again by the naked eye, or by, soon I'll call that a classical detector. And so here, for instance, now we come to a good reason why the crystals that I was mentioning at the very beginning are not an example of large entanglement, because the two states of the crystal, with or without this single excitation delocalized on this billion of ions, these two states cannot be discriminated or distinguished. Okay, so now here again this word of caution. One sees only photons, but unitary transformation from the crystal to photons, we don't see the crystal directly, we see the photons, but that's a unitary transformation, and the unitary transformation may change the nature of large entanglement. Okay, so we want also this distinguishability. So let's make that a bit more formal, and here actually I come back to almost the weak measurements, although just a noisy measurement here, and it's weak measurement without post-selection here. So it's very, very elementary. So the idea is just that we have we'll call a detector to be classical, or classical detectors, no photons in my case, also a detector which is only sensitive to the number of photons, so it is not sensitive to coherence, and with some thermal noise. I mean, our eyes are of that form. And because of the noise, it's not able to discriminate Fock states or photon number states. So you have your pointer here, you have your interaction Hamiltonian, so the P is the displacement operator for the pointer's position, and A dagger A, that's the photon number. And if there would be no noise and we send in n photons, we would just get the pointer at position n, but there is some noise, so we get something which is broader, and broader by some delta, capital delta. Okay? And now you have a typical example. Let's suppose, for instance, that we have this kind of superposition, n photons in the first mode, m photons in the second mode, superposed with the opposite, so m first, n in the second mode. And let's say n and m large enough that we could see them, so more than 100 photons like that. Of course, it then would depend on the wavelengths, but that's not relevant here. And very obviously, if n minus m is too small, it is impossible to discriminate them. If the difference is of the order of delta, you have a poor discriminability. If it is large, then you can really discriminate that. And you can, of course, make that quantitative. You can define this trace distance here, just as the average of the difference of the two probability distribution, absolute value. And the 1/2 here is such that when the probability of guessing, I will use that quite frequently also in the to present the experimental results here. So the probability of guessing, of course, I mean here guessing correctly, is 1 plus this d divided by 2, and then probability of guessing wrongly is 1 minus d divided by 2. And for these kind of states, the distance between them is this error function. Okay, it should be n minus m, absolute value of n minus m. That would be the case of m being equal to 0. Of course, it's invariant if you translate everything. So we have this idea that there should be some distinguishability or discriminability. I'm not exactly sure whether this is a proper English word, but I guess you can understand what I mean here. Okay, and if you have that, and you go to this typical state, so this is this curve here. It's the top curve. So here you have the number of photons, and here we have this probability of guessing correctly, assuming the thermal noise is 20, kind of reasonable number. So you see, of course, with 0 photons, you have you cannot distinguish, but already with 100 photons, you are almost at 100% probability of distinguishing. Okay, now let's try an example how we could do that in the lab. We're going to do almost that in the experiment then. So we start with 1 photon. And then we have a beam splitter, 50-50% beam splitter. So after that, we get this entangled state. So 0 photon, 1 photon, entangled with 1 photon, 0 photon. So of course, this is single photon entanglement, so it is certainly not large. And people may even argue whether this is really entanglement because we have only one photon and you need subsystems to be even talking about entanglement. But we have subsystems. The two subsystems are this optical mode, which might be an optical fiber in our case, and this is another optical mode. So we have two optical modes, and these two optical modes are entangled. But it's a very small entanglement. But now let's do the following. In addition to this single photon on this input port, we have a second input port, and there we put a lot of light, this coherent state, square root of 2 times alpha. But that can be large, whatever large you like, or you can make it. And we make sure that the two will arrive on the beam splitter at the same time, same polarization state, same mode, and same frequency also. So same frequency spectrum. Then they will interfere here. And that has also an effect that actually these 0 and 1, so the vacuum and single photon, get displaced in the phase space by a distance alpha. So the state that you now have is in the first mode, let's say the top mode, is the displaced vacuum, which is just the coherent state alpha, tensor the displaced single photon, plus the opposite, displaced single photon in the first mode and coherent state in the second mode. Now here we also very clearly have only one E-bit, so few or lower number of entanglement bits. But alpha can be large. You can make alpha 1,000 or million. I mean, in principle, you can make alpha large. So you have now entanglement between two optical modes, each populated by a large number of excitations, or photons. Now, does that count as large entanglement? For that, we need to make sure that the displaced single photon and the displaced vacuum can be distinguished, can be discriminated. No? And indeed, they can be discriminated using a classical detector, as I have defined it before. And they can be discriminated because the variance of the displaced single photon is about 3 times larger than the variance of the displaced vacuum. So the fact that one photon number distribution is much broader than the other one allows you, with some probability, I'll come to the exact numbers very soon, to distinguish them. Now the next point you could do is to put all these excitations in our quantum memory. So once they're in the quantum memory, you still have only one E-bit. So in terms of the number of E-bits, is still poor. But you have large number of excitations, this alpha square, and you have these billions of ions in the quantum memory. So you start a little bit to have something which is large. By the way, the basic idea here is due to my collaborator, Nicolas Gisin. Okay, here is this distinguishability to make more precise. So in red here, we have the case of so the photon number distribution of a coherent state, so the displaced single photon. In blue, you have the photon number distribution corresponding to this displaced single photon. And you see that the blue and the red one are quite different. So if you measure the number of photons and put the thresholds as indicated by these two dotted lines, the probability of guessing correctly is about, or goes asymptotically to 74%. So 74% is of course far from 100%, so you cannot distinguish them with certainty, but you can distinguish them, let's call that pretty well. And actually, so if you start from this entangled state, you can actually rotate the basis. This state is exactly the same as that state, where the state plus, so the ket plus and the ket minus, these are states which correspond to 0 plus 1 or 0 minus 1. And then the big state, let's say the psi minus and psi plus, are superposition of displaced single photon plus or minus the coherent state. And these two now, they have much larger differences in their probability distribution of photon numbers. So I think this one is probably with, I don't remember, the minus sign and the other one with the plus sign. I don't remember which one is which. But here now the probability of guessing correctly, just with a classical detector measuring the photon number, even if you have thermal noise, in the asymptotic limits, so if you go for very large alphas, much larger than the noise, you can guess them with almost 90% probability. So it's still not 100%, you still have some overlap here in the middle, but you see that the probability of discriminating them correctly gets significant.
A question. What is the input parameter that controlled this 74 and this 89?
Well, I mean, here, for instance, in this case, I measure the number of photons. If I get a number which is smaller than this value here, which is essentially alpha squared, smaller, I would bet on the blue case, because it's much more likely that it will be on the blue. If I get a number larger, I'll bet on the red one.
My question. I'm asking what in your model controlled that 89 and that 74?
There is nothing that controls them. I mean, there's nothing more than what is on this picture. There's no parameter. I mean, you just have two probability distributions. You need to distinguish them, and of course, whatever number you get, so you get one number here when you do the measurement, and you're going to bet on the most likely one.
It's a constant of nature? 74 is a universal... Right, so...
Right, doing the same thing on the left-hand side. So what about your detectors?
Well, here it is. So the detector is characterized by this capital delta. That's the noise of the detector. So these numbers that I'm indicating is the asymptotic case for large alpha. Of course, if alpha is very, very small, you cannot distinguish with some noisy detector. But whatever noisy detector you have, so classical detector you have, if you go to large enough photon numbers, you can distinguish these two states with these probabilities.
What would you change when it's that from the left to the right-hand side?
Well, once I'm distinguishing this state, the displaced single photon, from the alpha state, here I'm distinguishing psi minus from psi plus. I'm distinguishing two different pairs of states. But these two pairs of states that appear in this entangled state, actually in the entangled state it's the same. So this state is just the same as that. I mean, most states can be written in different bases. I mean, not most. All states can be written in different bases.
Do you change your photon detector?
No. No, but come on. I mean, that an entangled state can be written in different bases is not something new. Yeah, Harald.
I guess it's only about interference between a coherent mode with at average alpha photons in and a single photon at the beam splitter, and this determines the photon number distribution.
Yeah.
And this determines all this 74 and 89%. So it's only the interference.
Mm-hmm. No, they are not orthogonal. Oh, sorry. Yes, they are orthogonal. This state and that state are orthogonal, obviously, because this is the displaced vacuum, and displacement is a unitary transformation. This is the displaced single photon. So in the Hilbert space, they are orthogonal. But I'm not allowed to go and measure in the Hilbert space. I use only these classical detectors. And when I use classical detectors, I cannot probe everything in the Hilbert space.
So these psi plus one are not orthogonal.
Now these ones are also orthogonal in the Hilbert space, but when I only measure photon number distribution, I get distributions as indicated here that, well, I don't know what it means now, orthogonal for probability distribution, but clearly they have the same support. I mean, both support go, by the way, from 0 to infinity. Yeah, Gaussians with tails extending to infinity.
N and M that defines the delta.
I don't think I have an N and an M on this slide.
No, but previously you had.
I mean, I have only delta. Delta is the noise of the classical detector. Now you have a pointer, and this pointer has an uncertainty, like we heard in the previous talk with weak measurements. You have an uncertainty, and this is the uncertainty. There are no M, no N here. Okay? Okay, and now come back to this probability of guessing. Again, with a detector that has this amount of noise. Here, 20. And we have again here the photon number distribution from 0 going up. And let's say in the experiment we are close to 500, so we can go up to 500. So for instance, for 500, and so this was a curve for the distinguishability or the probability of guessing correctly for the state NM. This is the probability of guessing correctly for these two states, the psi plus and the psi minus. And the last one here, that's the distinguishability for the displaced vacuum and single photon, these two here. So this one goes asymptotically to 74, and this one goes asymptotically to 89. But in the experiment, we stop here, so I only show that part. And so it's not surprising that the more photons, the better you can distinguish. But interesting is, let's say if you're at 500, we can distinguish here with the same probability as if we had, in this typical example, the NM state, about 30 photons. It's about the square root of that one. So you can indeed have a state here which is as easily distinguishable by a classical detector as if you had a superposition of vacuum and photon number state with 30 photons. And 30 photons, now you say, is large or not large, that's just a matter of opinion, but certainly to me it sounds large because it's difficult to do. Okay, so let's now go really to large entanglement. We had only one e-bit, but actually there is a way to go to many e-bits. Instead of just sending one single photon here, I send a train of single photons. Can do that. And on the other input port, I send a train of coherent states. That's relatively easy to do. Then after the beam splitter, I will have this train of entanglement. So it's a product state. It's a product state of the states we had before. Okay? Now this is just a product state, so you may say it's not very interesting. But let's go then into these quantum memories. So all these excitations, all these photons, they all excite the same billion of ions in these two quantum memories. And so after these local unitaries of getting into the crystals, so inside the crystals, this is no longer a product state. It's a sort of complicated decay state with involved phase relations. So now inside here, inside these quantum memories, we'll have billions of atoms, thousands of excitations, or hundreds of thousands of excitations, and hundreds of e-bits. So this is unfortunately not the experiment I'm going to show to you because we haven't finished that, but we are working in that direction. But the idea is really to have now an example where we have not only large crystals, that's not the interesting thing. We have the many atoms, we have the very many excitations, because we have these many photons that are going to excite all these ions, and we can go to hundreds of entanglement bits. Then, of course, in principle, you should also be able to prove that you have entanglement, and for that, and so here we use really the fact that it's not large entanglement is not invariant under local unitaries. Now, going from here to here is a local unitary, is a local transformation, but it may change the nature of large entanglement. It's not adding entanglement, it's not removing entanglement, but it changes the nature of entanglement. And the same to measure them at the end, the easiest would be to take this large entanglement and again mix it on a beam splitter to do the displacement in the opposite direction. So you first displace it from the microscopic into the macroscopic world, but then you take your cat and you do all the operation backwards down to the microscopic, where you know how to do the measurements. And then here we can do indeed the measurements to prove that we have entanglement. Now this is a kind of interferometer, so it will be highly sensitive to phase noise. So it will be highly sensitive to this kind of decoherence. However, the nice thing here, and that's why we can do also experiments here, it is robust to losses. Losses is another form of decoherence. But it is quite robust to losses. For instance, the negativity, which is a measure of entanglement, decreases only linearly with the transmission. So if we lose half the photons, we still have half an e-bit. So we don't lose all the e-bits immediately. But high sensitivity here. Okay, so now let's go to the experiment. I have no idea how long I'm talking now. Oh no, there's a watch there. Good, good. So we need a source, and how do we make a single photon source? So that's a very standard technique. So we pump a nonlinear crystal and use here parametric down conversion to produce pairs of photons. And here we use a type 2 down conversion so that we get one photon polarized vertically and the other one horizontally, so we can split them with this polarization beam splitter. And one of them goes to this detector here, which is a heralding that announces the presence of a single photon here. So we prepare a single photon here. Then we send that to a beam splitter, our optical fiber coupler, and we get our single photon entanglement here. That's the very standard. Then we need to have this coherent state, and here we're not going to put the coherent state here and actually displace both. We are going to displace only one mode. So this mode will remain on the microscopic level, and this one only will get to these 500 photons. So this is done by using a beam splitter which is essentially transparent. So in our case, 90-10%. And doing that is a bit difficult because you have to make sure that this alpha state is not merely an elephant that you put next to your singlet. So here you have your singlet, and you could just have a bright beam, a bright pulse at a different wavelength. That would, of course, be completely cheating. It's like putting an elephant. So we have to make sure that this one arrives on at the same time, same polarization mode, and same spectrum as that single photon. And for the spectrum, the way to do that is actually not to use a laser to produce this coherent state, but to use, again, a similar nonlinear crystal, this piplin. But here it is spontaneous down conversion. Here we are going to use stimulated down conversion. So here we pump it. Well, we have the pump here, and we have also, in our case, it's telecom wavelengths. So in this sense, also, you cannot see it with the naked eye, but that's only a technical problem. We have a telecom laser here, which triggers the stimulated down conversion here, so that we get here now a coherent state which has the same spectral property as the single photon. And to make sure that we indeed have the same spectra, and also that we arrive at the same time here, what we do is here to introduce actually some attenuator, so that we attenuate this bright coherent state, and we have to make the assumption that this attenuator is just a gray filter, so it's not going to affect the spectrum. It should attenuate all the wavelengths and all the frequencies the same way. And then we can here do the standard Mandel dip. So we put a detector here, so single photon detector here and here. And we scan the delay, let's say by moving, for instance, this mirror. And we should see that when we are at the same time, provided we are in the same polarization and same optical frequency spectrum, we should get a dip. And we see the dip, so the red dots are the experiments. And the blue one, I really want to emphasize that there is no fitting parameter. The blue one is exactly the theory, taking into account that this being not a single photon, but is a coherent state, so with Poisson number distribution. And also this is not a 50-50 beam splitter, but a 90-10 beam splitter. So one expects exactly the blue curve, and you see that the red experimental dots fit perfectly. So we have indeed not an elephant, but really a displacement going on here. Okay, so at this point now we have this macroscopic entanglement, or macroscopic entanglement. And then to do the analysis, we displace it back. So we have the displacement in the opposite direction, which just means there must be a pi phase on the second coherent state. And then here we are down in the microscopic level where we know with avalanche photodiodes how to do all the measurements. And we measure here the concurrence, which is a measure of entanglement, which involves visibility and probabilities of these different counting rates. And so here we see for how large our photon number of the coherent state is. So the mean photon number of the coherent state. So for 0, we get some significant concurrence. And when it goes down, if we go up with alpha square, with the mean photon number, but you see that at 500 photons, we still have a positive concurrence. So we still have some entanglement. Admittedly, very little entanglement, but still a bit of entanglement here. And just to show some more experimental results, so we measure the visibility, which of course for low photon numbers is essentially 1 and goes down. So this is the sensitivity to the phase. And then you have also to measure the probability of having 1 photon 0, 0, 1, 1, 1, and so on. And you put all that into this formula for computing the entanglement. So now if I come back to this kind of presentation, now I'll try to change a bit the presentation. Still photon number here, so going up to about alpha. Let's suppose we are satisfied with a probability of guessing of 80%. Now, if we say that we are satisfied with 80% and we have 500 photons for the coherent state, then we know how much noise our detector must have. So it fixes the delta. And fixing the delta tells us also how large this effective size, n minus m. You remember that is the entanglement between Fock states. So where we are here with 80%, if we accept 80% as a probability of guessing correctly, we have something like 30, 35 photons in difference between our two components. So does that count as large entanglement? And I'll give two answers. The first one is yes. Yes, because we demonstrated entanglement between two optical modes, one populated by up to 500 photons, and the involved quantum state of these 500 photons can be distinguished with classical detectors with probabilities, asymptotically 89%. We were a bit lower, of course. So in this sense, I would say, yes, we have demonstrated large entanglement, but of course, the opposite view can also and equally well be defended. Well, first of all, there's only a very small amount of entanglement, much less than even 1 EBIT, so there's certainly not many EBITs. We still have a lot of work to do that. We only have 2 parties. I guess that's okay for the time being. There's no distance or very short distance. That's okay. And so far, we didn't went into the crystals, so we are not yet in with massive particles. And actually, going to massive particles will imply for us changing the wavelength, so it's not a trivial change. However, I think if we would be able to do that, as I have already showed, then we would really be able to show truly large entanglement. Decoherence. That is certainly, Serge Arash is clearly not here, but he would certainly talk about decoherence, obviously. And there are many types of decoherence, and our type of entanglement is quite robust to losses. And again, I think one shouldn't be negative with that, because if we want to be able to do any kind of experiments, it must be that the system that we are investigating experimentally shows some robustness. If there would be no robustness at all, then it's just impossible to make the measurement, almost by definition. So I don't think there's anything wrong. I think, on the contrary, to find a case where you can have large entanglement robust enough that you have the time to do a measurement is a value. Although sometimes I get that as a criticism. I think it's a value. On the other side, our entanglement is highly sensitive to phase noise. And I think there is a general, we are now working with the student, Sekatsky, to analyze that, because I think this phase sensitivity is necessarily present in all examples of large entanglement, if we define large entanglement as I did today, just because photon numbers, I define large entanglement with photon numbers and my classical detectors, but photon numbers and phase are conjugated variables. So I think there is a very general rule here, lesson here. I'm probably at the end. So, okay, are there quantum opticians here? Yes, there is Harald. So for these ones, they're going to tell me that the large entanglement should be this kind of Schrödinger cat state that quantum opticians since years call a Schrödinger cat. And clearly, this kind of state is not at all large entanglement in my definition. So if you want to discuss that with me and argue, we can do that afterwards. So the conclusion is, well, we have this large entanglement defined the way I did, has many facets. I'm certainly not claiming that my definition or my approach is unique, or is not even claiming it's better, but it's one possible one. It's a sensible one. That's what my claim. This very important lesson, which, well, confused me for a long time, is large entanglement is not invariant under local unitaries, and we could demonstrate it, at least pretty large, or whatever you like, with this efficient size of about 30 photons. And we're going to learn a lot by playing with large entanglement. Okay, thank you very much for your attention.
I would like just to ask you, which is the G2 of your heralded photon source if an eventual multiphoton component would influence your analysis? And the second question is, how do your results compare with De Martini's results about the multiphoton entanglement? Yours seems much more clean, but...
Yeah. Okay, so for the first question, the G2 value, I don't remember by heart, but I know it's very small. In this heralded single photon, you can pretty easily go to very low G2s. So I don't know the number exactly, but 10 minus 3 or something like that, that order of magnitude. So this is not an issue, a real issue here. The second question, how does that compare with De Martini's cloning? So there is some inspiration, and as you know, we had a heated debate with him and even agreed at the end, which is quite an achievement. The similarity is that he also had this idea, you start from microscopic, so 2 photon entanglement, and then by cloning one of them, you bring it to the large, to the macroscopic world. So this is clearly similar. But the difference is that in his case, there was no classical detector, no measurement using classical detector that was able to discriminate between the 2 components. So he was missing this discriminability that we have. That's the main difference.
I'm also puzzled by the statement large entanglement is not invariant under local unitaries, and then I'm more puzzled because you presented concurrence, and concurrence is a measure of entanglement. It's invariant under local unitaries. So I think you presented more an entanglement witness.
No. So the argument is that, so we have these 2 modes, which are populated by 500 photons. Now, how do you make sure that they are entangled? And now we go to entanglement theory. We say by doing a local unitary, we cannot increase the entanglement. So we bring them down to the microscopic world, and by that, we change, it's no longer large, it's microscopic, so we change the nature of large entanglement, but we for sure don't create entanglement. And once we are down at a single photon level, we measure concurrence. So we measure classical, well, a standard, not classical, but standard entanglement witness. And by that, we measure, we lower bounds the entanglement in the original microscopic entanglement. Because it's not by going by these local unitaries, we could not create entanglement. So what we measure at the end had to be there already from the beginning.
High entangled systems from many systems with low entanglement. At the end, you have a system of lower dimension with higher entanglement. Is it a way to see the process?
I don't think so. Well, according to the theory, so suppose forget losses and all experimental inefficiencies or limitations. The number of entanglements, or quantity of E-bits, should be 1 throughout the entire experiment. It's 1 from the first beam splitter until the very end. So in principle, it should be 1 all through. Of course, experimentally, we don't find 1. We find significantly less than 1, but still positive.
You determine concurrence, but what happens if you have entangled states in 3 states or 4 state systems? There, as far as I know, it is not clear what could be used or what could be defined as a measure of entanglement.
Yeah, I agree with you, but that's a kind of different question. Indeed, we don't have, let's say, one universal measure of entanglement for all situations. But again, here we used 1, a very well accepted one, which indeed is valid for 2 parties and for qubits. And so we could demonstrate entanglement. Clearly, if we go to 10 crystals, which we're not close to do, but I mean, if someday we do it with 10 crystals, we hope that the theorists will have in the meantime enough progress that we can also do that.
Do you know if those experiments put further bounds to the GRW collapse parameters that we heard about this morning?
Well, I know about them a bit, yes. I mean, is that the question? Yes, when the answer is yes.
No, like, the question was rather at what orders of magnitude are we talking about in the scheme presented by Angelo or by?
Yeah,
by
well, I guess,
Ulrich?
so for instance, you could ask this, when I tell you we have a billion atoms that are entangled, that sounds a good candidate to test GRW, no? However, this entanglement is of not at all of the GHZ form, but it's a W state. And the W state has, the value of being quite robust to losses. So if we lose one qubit, it's essentially undisturbed, the W state. But then, of course, it also means that to test GRW is very bad, because if there is a collapse, a heating process on one of these atoms or ions, it would essentially be not observable. So it's not a good state to test GRW.
Right, thanks.